Hello, everybody. In this video, I'll go over those 11 questions on practice test number 5. So you should at least try to do the problems, those 11 questions on practice test number 5 in Calculus 3, and then use this video to go over some of the problems that you may be having. And at the end, I will be discussing and adding a few comments about the differentials. What is D capital S? Is that different from D capital S with a bar on top? What's dr? How is that related to ds and dt and so on? Okay, so that's what I will do at the end. But let's start with those 11 questions on practice test 5 first. Okay, so this is your practice number 5, right? And I hope you have printed this out and you have at least attempted to do all, if not most of the problems, okay? So number 1, you are given a real valued function, which is x plus y. This is two-dimensional, but it's real valued. And the C is the portion of the circle, x squared plus y squared is equal to 36 in the first quadrant. So you should have a picture at this point, and in your mind, or maybe just, on your piece of paper, I am actually a big proponent, and I highly encourage you to draw a picture whenever possible, because it's much easier to see things if you can draw it first. So you are having this radius 6 circle centered at the origin, but it says the first quadrant, so you can just draw a quarter circle from 6, 0 to 0, 6, right? And so at this point, you should have this at least in your mind. And then you are to evaluate this line integral. All right, so think about, think of this, what's happening in your brain, like when you read this, right? You realize this is, instead of saying, well, I have no idea how to even start, okay? This is a real value function, and you have this curve, C, and so this is a line integral, right? And line integral, what is the thing that you have to do with this ds? Remember, we don't use ds in actual calculation, we use t. So that should remind you, oh yeah, I have to use t. So the first thing you should do is to come up with a parameterization of this quarter circle. And since the radius is 6, you should use 6 cosine t and 6 sine t as t goes from 0 to pi over 2. And then what do you have to do? Yeah, you have to think of this, right? You have to take the derivative, and then you take the norm of it. Why? Because this ds happens to be equal to that. Okay, so once you remember that, you should have no problem doing this question. All right, so I'm going to switch to the answer key, which you already have available in your Canvas shell. All right, so this is the picture. You see that I have already parameterized this quarter circle. All right. And then, of course, t goes up to pi over 2. You take the derivative, and then you take the magnitude of that velocity, which is called the speed. Now, speed is constant in this case. It's 6, all right? And then you have this function, which was x plus y. But remember, you can't use x and y anymore. You are basically moving from the world of x and y into the world of t, all right? Everything has to be written in terms of t. So x is this, of course. Y is that. So x plus y is 6 cosine t plus 6 sine t. That's what you integrate. This 6 is your speed, which it's a part of your ds, right? And then, of course, you have you can factor out these 6, and then you take out that 6. That's 36 in front, and then you integrate cosine. That would be sine. And the integral of sine is, of course, inverse minus cosine, and your answer should come out as 72. No problem here, right? I hope you got that one easily. Okay, so let's go to number 2. Capital F, now you notice here, this is a vector field, right? So the vector field is negative 3z, 6z, 6x, and 6y. Again, think of, what the first step is, and try to, think ahead. And then you have C, which is a straight line segment from 0, 0, 0 to 2, 2, 2, okay? So you should probably parameterize that. Find the work done by F along C. So what is the work integral? All right, that's what you should be thinking about. And I hope you remember, well, okay, so first it is the tangential component added together or integrated together. But if you remember, this work is associated with the president associated with the New Deal, and that is FDR, and that's what you write, FDR, right? And then you should remember this is calculated by F dotted with R prime. You no longer need that speed because that part cancels out, right? And so this is what you need. So at this point, you should know, oh yeah, I have to write F in terms of X, T, and then you parameterize R and then find R prime. The next thing you have to do is to actually parameterize this. Now it's a straight line segment. So what would be a good one? T, as T goes from 0 to 2 would be okay. You can also do 2T, 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 as T goes from 0 to 1. That's okay too. Remember, it's a part of the line, so this will be a line equation. Like X is T, Y is T, Z is T, or X, Y, Z are all 2T, or something like that. All right, and then you take the derivative of that, you take the dot product of F and R prime, not R, but R prime, and then you integrate it. All right, so let's see what the answer key looks like. So here I first write copy F, right? So in this example, or in this key, I am using 2T, 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 okay, as T goes from 0 to 1. And so the derivative is 2, 2, 2. You take the, you write F in terms of X, Y, Z. Notice here, this is X, this is Y, this is Z. So negative 3Z, which is your X component, is negative 3 times this. That's negative 6T. And then 6x, which is the second component, is 6 times 2t, which is 12t. And then 6y is 6 times 2t, which is also 12t. This may be a little confusing thing because you have, 3 components, but I don't think it's going to be too difficult. All right. And then you take the dot product of f and r prime. That's simple. That's this thing here. It's not a vector anymore, right? And this adds up to 36t. You integrate from 0 to 1, you get your 18. So hopefully this was not too bad. All right, number 3, you are given the vector field, and this looks like a complicated one. And then C is any path. Okay, so as soon as you see that, you say, all right, C doesn't matter as long as you go from one point to another. You should say, oh, this must be a question involving which theorem? Now, if it says any path, that means the vector field must be path independent. And that means it's conservative. And that means you have to use the fundamental theorem of line integrals, right? Yeah, so you must use that one. First, show that f is conservative. There is a way to do that. And then use the fundamental theorem of line integrals to evaluate this. Remember what this is? This just depends on the it just depends on the beginning and end points, right? So once you find that potential function, lowercase f, this is what you do to find the answer. So that's good to know because it tells you to use the fundamental theorem. Now, how do you check this? Okay, remember this is PQR, right? So you have PQR. And then what you can do is you can write XYZ and you compare the partials, all right? 3 sets of partials. First, you have to show that QZ is equal to, well, let's see, let's do this in right order. PY must be equal to QX, all right? And then the first and third, PZ must be equal to RX, and then last two, QZ must be equal to RY. So that's what we'll do. I think one of them is a rather complicated partial, but that's the intent, right? And once you find that, you find this lowercase f, a potential function, by integrating this with respect to x, this with y, with z. All right, and so let's go ahead and do that. So here is the answer key. Now, what do you see here? That's number 2. Number 3, so you have P, Q, R identified as the first, second, and the third components of that vector field. Okay, now remember, you are to do this, P, Q, R, X, Y, Z. So let's first look at PY. Now, PY is a little tricky because you have to, right away, you have to use what? The product rule, okay? So the product rule says it is the derivative of the first with respect to y, which is 1, times the derivative, times the second, which is just e to the xy, plus first y times the derivative of the second derivative of e to the xy with respect to y. So I hope you understand that this x is acting like is a constant. So x comes to the front, and then e to the xy, of course, stays. So this is your py. And then qx is, you take the partial of this with respect to q, and again, you have to apply the product rule. So it's the derivative of the first, which is 1, times the second, e to the xy, plus x times the derivative of the second, where y is now acting like a constant. So it's y e to the xy. Notice here, these are equal to each other. Good start. Okay. Next, it's pz and rx. Well, pz, or p has no z, and r has no x, so they are both 0. Nice, right? And then finally, qz and ry. Qz, you take this with respect to z, that's 2z, that's easy. And then that was qz, then it has to be equal to ry. You take the derivative of that with respect to y, and you get 2z. All right, so these three equations together tell you that the vector field PQR is indeed conservative, and that means you can find the potential function. How do you find the potential function? Lowercase f, right? F is a function, a real valued function, depending on x, y, and z, such that its partial with respect to x is this, and with respect to y is this, and with respect to z is that, right? So if you integrate the first one with respect to x, ooh, that's a little complicated, isn't it? But I hope you understand that the antiderivative of that with respect to x is simply e to the xy. Just differentiate this with respect to x. You can see that it would be y times e to the xy with the chain rule. You could also have some expression involving y and z, but x should not appear here, right? If you differentiate f with respect to q, then you get this thing here. So that means you should have e to the xy, because the partial of this with respect to y is exactly x times e to the xy. But you also have this. That means you have to have yz squared somewhere in this expression of lowercase f. And then you may have some other expressions involving x and z and constants, but no more y. This is now the next one. R is the derivative of lowercase f with respect to z. So all that means is you should have yz squared, right? And some expression of x and y, but no more z. So now you don't add them, by the way. You don't add these terms. All you have to do is to find one function, lowercase f, which looks like all of them, okay? So clearly e to the xy has to be that. And yz square has to be there, right? And in fact, that's all you need. I mean, you may have a constant, but you can't have any more x in here because that should show up here. And you can't have any more y because that would show up here. And then you can't have any more z because that would show up here, and so on. So this is your potential function, all right? Once you find the potential function, you evaluate that at the top, the beginning, I mean, at the terminal point, which will give you 1 raised to the, e raised to the first power, plus 1 times 1 times 1. So it's e plus 1. If you plug in zeros, you get e to the 0th power, which is 1, that one, and then plus 0 times 0 times 0, which is 0. So the answer is e plus 1 minus 1, and that is e. And that is a solution for part 3. All right, number 4, define the vector field f. It's defined on the plane as x squared plus y squared, comma, x minus y. Ooh, that's two-dimensional, okay? Use Green's theorem. That's good because Green's theorem only applies to two-dimensional, pictures. And evaluate the line integral. All right, so that means you have, because you're using Green's theorem, the line integral has to be a simple closed curve, or the line has to be a simple closed curve, and you're supposed to find the line integral, FDR, over C, which is, oh, it's a rectangular loop. So it doesn't look like the thing I just drew. And then starting at 0, 0, 2, well, let's see, 2, 0, and then goes to 2, 4, and then to 0, 4, and comes back to the origin. This is a 2 by 4, not a 2 by 4 in the sense of, you know, piece of wood, but it's a 2 by 4 rectangular region. And the region R is this inside. And you know what to do with Green's theorem, right? That's a theorem that tells you this line integral over the simple closed curve boundary is the double integral over the region of Qx minus pay, Qx minus Py, which happens to be called the curl of this vector field f of xy. All right, so let's take a look at this. You have to find Qx and Py, and you have to integrate and use the double integral. Here's the answer to number 4. Qx plus minus Py is actually easy because Qx is just 1 and Py, as you can see, is 2y, right? So 1 minus 2y is what you have to integrate over this region. And so you go, x goes from 0 to 2, y goes from 0 to 4. This is the integrand. This is like, you know, your simple calculus problem. And so if you integrate the first part, it will give you, this will become y minus y squared. Plug in 4 and 0, it'll be negative 12. And negative 12 times the integral from 0 to 2 dx, that's 2. The answer is negative 24. Next, question number 5. Let C be the unit circle. All right, so let's picture the unit circle, radius 1, centered at the origin. I am so nice that I actually define for you what the unit circle is, even though the unit circle means the same thing all over the world. Okay, oriented counterclockwise. All right, so you're going in the regular conventional orientation, and then you are given this f. Okay, again, two-dimensional. Use Green's theorem. It says verify use Green's theorem. So that means you are to show, you are to show that this one side, you have to calculate this side, and you have to calculate the other side. It's very important for you to be able to write down these, you know, standard equations or the statements of these theorems, especially the theorems with names like Green's or Stokes or the divergence theorem. And just go ahead and, you know, learn how to write the expression or the equation that is the statement of each theorem. And you are to show calculations on both sides. So I have to do this problem and this problem. Wow, this is a one problem with two parts. Okay, so let's go ahead and do that. I have this unit circle. You know how to parameterize the unit circle. This side is just going to be, well, you know, this is my P, this is my Q, but Qx minus pace, it looks like it's a really easy expression. That's 6 minus Py is 4. Ooh, that's 2. So you know this side is really simple. It's 2 times the area of the circle, which is pi, right? Okay, so let's look at the answer for number 5. Not surprisingly, the parameterization of the unit circle is cosine t, sine t, as t goes from 0 to 2 pi. F is copied here. The derivative of the parameterization is given. And f is written in terms of x and y. Well, remember, this is x and this is y. So x plus 4y, for instance, becomes cosine of t plus 4 sine of t. Do the similar thing for the second component. Then you take the dot product of these two, f and r prime. Things cancel. You can do this on your own. And then, ooh, you have a negative 4 sine square and 6 cosine square. Okay, now do I, am I supposed to be, do you have to know these things? Am I going to ask you questions like this? Well, you know, although I do expect you to still remember the integral of cosine square is 1 plus cosine 2t over 2t, 2, but you would not need to remember that. On your tests, as I indicated in my solution key, you will not need to know the integral of cosine square or integral of sine square. Okay, it just so happens, I mean, you can look up these things if you want. These come, both of these actually come from the two different ways of writing the double angle formula for cosine. Okay, but assuming that you have already learned to do this in calculus 2, I will not hold you responsible to do this. But since this is your practice test, look it up and find your answer. Okay. I, in this case, canceled the denominator and the numerator, write this as a 3. This part is easy to integrate. And by the way, sine 2t and cosine 2t, both of these, I guess it's sine of 2t. That's a periodic function of period pi. So, sine of 2t is going to be exactly the same when if you plug in 0 or 2 pi, 0 or 2 pi. So this part basically goes away, okay? And all you need is 3t and then minus 2t. That's 1t. And then, of course, you go from 2 pi to 0, right? And so the answer will be 2 pi. So this part is not so difficult. The other side, the right-hand side is much easier because you already calculated that qx minus py is 2. So this is basically twice the area of the circle. So that's 2 times the area of the unit circle, which is pi. So it's 2 pi, right? And they are equal to each other. And thus, we have just verified that the Green's theorem is true for this specific situation.